Hello everyone, let's look at this time what exactly the RS decoding. Earlier we have seen what is RS encoding, how the format of RS code is slightly different than the BCH code. So as we have seen, the BCH codes are the binary codes which are nothing but again the cyclic codes itself. Now RS code is again the binary but non-binary cyclic code. So for discussing what exactly the RS decoding, let's take the help of one of the problem statement. So I will just go for reference of one of the problem which was asked in the university question paper for almost 9 marks. So we will discuss this problem. So it is asked in the problem statement, design a 7,3 read Solomon double error correcting code. So from this very first line it is quite clear. N is given as a 7, K is 3, and it is read Solomon, that is RS code. TC is given as a 2. Find the systematic code for the message alpha, alpha cube and alpha raised to 5. Now from this second line it is quite clear. It is asked to find out systematic code, means systematic RS code for the message, means the data alpha, alpha cube and alpha raised to 5. The received symbols are as below. Now for the given received symbols, this first and second one, these are nothing but the coefficient of the received code word. We need to obtain the corrected code word. So let's discuss it for the very first case, means for this alpha raised to 0 till alpha raised to 5. What exactly the case? Now before proceeding to the decoding part, it is quite demand for this problem statement to proceed with the encoding part. Now encoding means ultimately we need to obtain the correct code word which is to be transmitted, and decoding which is related to the finding the corrected code word with the help of the usual statement which we used to follow from the LBC till the BCH, that is C of x is equal to E of x plus R of x. Now let's discuss this very first case, but before that we will proceed with the encoding part. So as the encoding part demands for some of the calculation of the g of x. Now for proceeding with the g of x, firstly we should know for given value of n as well as k, what is the value of m, which will decide the ultimate primitive polynomial. So from value of n, we can easily obtain m with the help of the log n plus 1 to the base 2. From that one we will get the value of m as a 3. Now if m is 3, for this m equal to 3 case, we will have this primitive polynomial, that is x cube plus x plus 1. Now equate it to the 0 by putting x equal to alpha, means replace x by alpha and equate to the 0. Once we equate it with the 0, we will get this kind of values, means CF. F of alpha equal to 0 means alpha cube plus alpha plus 1. This entire polynomial will be in terms of alpha equal to 0. So this is giving the value some sort of equation. Alpha cube is equal to 1 plus alpha. Here, with the traditions of the maths, we can proceed it to write it as a minus 1 minus alpha, but that is not the case in case of either non-binary or the binary codes. So that's why it has to be replaced with the minus 1 as a plus 1 and minus alpha as a plus alpha. So for finding alpha raised to 4, multiply this alpha cube by alpha, so that you will get alpha plus alpha square, means alpha into 1, that is alpha, alpha into alpha, that is alpha square. Again to get alpha cube, alpha raised to 5, we will multiply this alpha raised to 4 by alpha. So it will give alpha plus alpha square into alpha. So after multiplying this particular term, means this entire part by alpha, obviously we will get 1 plus alpha square. Why this is 1 plus alpha is coming? Because alpha square, this will be the term, alpha cube will be replaced by 1 plus alpha. So that is why this will be the proper substitution for alpha raised to 5. Alpha raised to 6 means again multiply this alpha raised to 5 by alpha. So it will give alpha plus alpha square. So alpha plus alpha square will be replaced with certain values. Next is alpha cube. So alpha cube will give the value as a alpha plus 1. So alpha and alpha both will be cancelled from alpha cube as well as from here. So next replacement which is been remained over there, that is nothing but alpha square plus 1. So that's why for alpha raised to 6, this is what the proper substitution. Alpha raised to 7 will follow the same kind of nature as that of alpha raised to 0. So that's why it is 1. Now once we got all these values, next we can proceed to get the g of x. As we have seen in case of the encoding part, the g of x will have the roots as alpha, alpha square till alpha is to 2tc. It means we can just vary the powers of alpha. That is alpha is to 1, 2, 3 till 2tc. Tc is equal to 2 for this particular case. So it will give x plus alpha raised to 4. So after multiplication of all these terms, further simplification with the following of this particular Galois field table as well as the simplicity of the related polynomials in terms of the alpha, it will give this final value of g of x. Okay. So this final value of the g of x will be used for the encoding part. Means here itself we are not going to stop. We need to obtain a systematic code. So format for the systematic code is already known to us. That is nothing but p of x is equal to x raised to n minus k dx plus p of x. Let's look at the same. For finding the systematic RS code, this is what the given terms. Actually, these are nothing but the coefficients which are given to us. That is alpha, alpha cube, and alpha raised to 5. If I want to represent this in terms of either d of x or m of x, it will be written like this. So here we are just varying the powers of x. So this alpha is actually the coefficient of x raised to 0. Alpha cube is the coefficient of x. Alpha raised to 5 is the coefficient of x square. Once we got this, next thing is to obtain c of x. So for c of x, this is what the expression for systematic RS code. The same kind of expression already we have seen in case of the cyclic code. Now, since these are the subclasses of the cyclic code, the same sort of nature can be applied over here. Now, n minus k, for our problem statement, it is given that n is 7 and k is 3. So obviously x raised to 4 m of x or d of x means multiply x raised to 4 to this entire d of x, that is the data polynomial or the message polynomial. So this is what the term we will get after this x raised to n minus k dx. Now the next operation is quite important because here only by calculating this half part, the c of x is not completed. We need to obtain p of x also. So for getting p of x, let's proceed with the steps. So this is what the g of x earlier we got, and this is what the x raised to n minus k dx. Once we perform this division operation, then whatever the remainder we got, this is what the remainder, and this is also called as a remainder polynomial. Now here the simplification is actually required because we intended to go single value of alpha as a coefficient for any, let's say, the x term. So alpha raised to 7 will be alpha raised to 0, alpha raised to 5 plus alpha cube. This will give me the alpha square. If we just take this earlier table and try to obtain what exactly the alpha raised to 5 plus alpha cube, let's look at this table. Alpha raised to 5, if it is added with alpha cube, it will give me this particular addition. If it is done with this, 1 plus alpha, 1 plus alpha will be cancelled and only this alpha square term This is what the term we will get. Now once we got this alpha square, it can be substituted over here. So that is for this particular term, we can have a substitution. So for alpha cube and alpha raised to 5, when these two are added, this is what the substitution we will get. Same is to be applied for this alpha square plus 1, because alpha raised to 7 is nothing but alpha raised to 0. So alpha square plus 1, just look at this table and we will get alpha square plus 1, it is nothing but alpha raised to 6. So the same kind of technique can be applied. So that is how we will get alpha raised to 6 for this entire substitution. Now once we got this p of x, now the job is still not done. This p of x has to be added with x raised to n minus k dx, means this particular term. This is nothing but the value of, you can say, x raised to n minus k dx. We add it with this p of x, then actually our job of calculating the c of x is completed. Let's check it, how to do this particular operation. So this is where we added it. This step is just to add it and obtain it. Once we got it, related coefficients are simply reflected here. So here the coefficient will be provided. So alpha raised to 0, this is for 1. Alpha square, that is for x. Alpha raised to 4, that is for x square. Like this it will be provided for all the values. Now the received code is given as, okay. Now here the decoding parts is getting started. This is where actually we just got the code word which is been transmitted. Okay, this is value of c, which can be obtained from c of x just by writing the coefficients, nothing else. Now once this is done, we will proceed with the decoding part in a slightly different way. But to know all these factors, just try to refresh. What are the decoding steps for the BCH code? As almost 90% part of the BCH decoding is same as that of the RS decoding. So here we are going to follow the same kind of steps. So step number 1 was calculating the syndrome with respect to the TC. If it is given, that is fine, but if it is not, then it's the job to be done. For our case, fortunately we have the TC is equal to 2, that is given in the problem statement itself. So the related syndromes, first of all we need to obtain. We need to check for the next step whether the non-singular matrix, means the determinant of whatever the syndromes we got, whether it is not equal to 0. So if this is satisfied, then only we can proceed with the given value of TC. Otherwise, if it is equal to 0, we need to decrement the given TC. And ultimately, we need to follow the steps to obtain the error locator polynomial. But let's proceed for getting all these things. So here R is given. For the first case, the R is given alpha is to 0 till alpha is to 5. Now we will just represent this R with respect to the R of x. For representing it, alpha raised to 0, x raised to 0, alpha square x, then alpha raised to 4x square. This is how the entire R of x can be obtained. But by getting R of x, still it is not surety that you are getting the corrected code word. But this problem is actually giving the encoding as well as the decoding combinedly. That's why it is quite easy to compare it with the, we can say, the coefficients directly over here. This is the transmitted code word, this is the received code word. 0, 2, 2, 4, 4, 6. This is 0. then alpha raised to 6, then alpha cube and alpha raised to 5. Means ultimately here we can say it is giving some sort of errors over here. Our job is to correct it. Let's proceed to obtain the syndromes first of all. So for calculating the syndrome, in a decoding, the very first step. So for getting the syndromes, this is what we need to do here. For obtaining, let's say, the first syndrome, S1, if we just observe this expression carefully, it is Si is equal to R of X by putting X is equal to alpha raised to I, where I is ranging from 1 to 2 Tc. Means for our case it is 1 to 4. Okay. So S1 will be R of alpha, S2 will be R of alpha square, S3 will be R of alpha cube. So wherever X is there, we'll replace it by alpha for getting R of alpha, that is S1. Wherever X square, sorry, wherever we replace the X by alpha square, we are actually calculating R of alpha square means the second syndrome. So this is how this entire expressions can be solved for getting the related syndrome. So S1 will be alpha cube, S2 will be alpha raised to 5, S3 will be alpha raised to 6, and S4 will be 0. So for all this, it is quite sure that when you want to calculate, let's say alpha raised to 10, it means it is nothing but alpha raised to 3. When you want to calculate alpha raised to 8, it will be simply alpha. When it is alpha raised to 11, we need to take the value as a alpha raised to 4, because ultimately we are finding it for n equal to 7 case, means gamma spin of 81. Okay. So that's why let's proceed by calculating all these syndromes, how the things are going on. Once we got S1 to S4, now the job is slightly critical to get the calculations for lambda 2 and lambda 1, which are nothing but actually the you can say the elements of error locator polynomial. Now let's proceed to calculate it. Now first of all, we are going to check whether this determinant of S is not equal to 0. Now by obtaining it, it can be treated as a determinant of M not equal to 0. So if you just verify by putting this S1, S2, S2, S3 and just cross check its determinant, you will find that when we put these values alpha cube, alpha raised to 5, this is giving the value which is not equal to 0. So ultimately we can proceed with the value of P as a TC, which is nothing but for our case as a 2. So once we go on putting these values, we will obtain here the cases like by the reference of BCH decoding equation number 7, we can easily obtain what exactly this format. Now here I want to calculate, let's say, the lambda 2 and lambda 1. So obviously we need to obtain the inverse of this one. But before that, we need to cross check whether the determinant of this part is not equal to 0. Right now it is not equal to 0. So we can proceed for the further calculation. So to get lambda 2, lambda 1, take the inverse of this matrix, multiply it to S3, S4. So inverse of this matrix that can be calculated either by this method, or it is also called sometimes as the adjoint of matrix M. So for getting the adjoint of matrix M, just invert these diagonal elements and change the sign of these diagonal elements. That will give the adjoint and divide it by determinant of. So by putting the values of S1, S2, S2, S3, okay, and afterwards inverting it so as to get, see here, alpha raised to 6 and alpha cube, these will be interchanged to get the cofactor, or it is called as a adjoint of M. Now once these are interchanged, later on we'll just obtain the determinant of M. So it will be given like alpha raised to, let's say, 9 plus alpha raised to 10. So alpha raised to 9 means it is nothing but alpha raised to 2, and alpha raised to 10 means it is alpha raised to 3. So by solving it, this will give some sort of simplification over here. So it will be alpha raised to 9 will be alpha square, alpha cube will be replaced by alpha plus 1. So replacement for this entire thing for alpha square plus alpha plus 1, this is nothing but alpha raised to 5. So that is what written over here, alpha raised to 5. So let me just clear it. So once we got this alpha raised to 5, now the job is, let's take it as a invert so that we can multiply this alpha raised to minus 5 to the inside term. Directly one may go for the multiplication so as to get this term. So directly I will go for this term. So alpha raised to minus 5 into alpha raised to 6, it will be alpha raised to 1. Alpha raised to minus 5 into alpha raised to 5, it will be alpha raised to 0. Again here alpha raised to 0. This is alpha raised to minus 2. Alpha raised to minus 2 means for Galois field of 8, it will be minus 2 plus 7 means alpha raised to 5. So ultimately this is what the matrix we can say the value for M inverse. Now once we got M inverse, just multiply it with the right side part, that is S3 S4. So we got this M inverse. This is what S3 S4 values. So after multiplication, alpha raised to 1 into alpha raised to 6, that is alpha raised to 7. Next alpha raised to 0 into 0, that is 0. Next alpha raised to 0 into 6, alpha raised to 6 means it is alpha raised to 6, that is what the value. Next it is 0. So this is what the values we are getting. Alpha raised to 0 can be written as alpha raised to 7. So that is why it is provided here as alpha raised to 0. Next is alpha raised to 6. So lambda 2 and lambda 1 both are obtained with the values of alpha raised to 0 and alpha raised to 6. By getting these values, since the error locator polynomial is lambda x is equal to lambda 2 x raised to 2 plus lambda 1 x raised to 1 plus 1. So this is obviously the 1. So lambda 2 is nothing but alpha raised to 0, lambda 1 is alpha raised to 6. By using the reference of lambda x, that is error locator polynomial, we can easily obtain it. So with the help of G of 8 table, we need to obtain here the error locations. So how to go for this? So there is one balanced error solution which is provided by the Chan search. So he proposed that method where we need to obtain the powers of alpha, which will give ultimately the product to solve the quadratic equation kind of thing. So see here. So here alpha raised to 3, that is 1 plus alpha. If I take alpha raised to 4 as alpha plus alpha square by the following GF of 8 table, then obviously 1 plus alpha cube x and 1 plus alpha raised to 4x. If we multiply these two, we get this kind of expression, means alpha cube plus alpha raised to 4. It is nothing but this particular statement by cancellation of alpha and alpha. We will get 1 plus alpha square, that is alpha raised to 6. Let's press the Galois field of 8 table. Okay, so once this is done, it will simplify that these powers, that is 3 and 4 for alpha, these are nothing but the error locations. So here we can just check out that error is in the third and fourth symbol, which can be tracked at the initial stage only, because this problem is the group of encoding as well as the decoding. Now afterwards we can proceed with y1 is equal to alpha cube to represent this 3 and 4 with y1 and y2. Now to correct these errors, we need to go for certain operations over here. Now these equations will be written in a slightly different over here in case of the RS decoding. So it will be written like S1 is equal to R of alpha, where E1 Y1 plus E2 Y2, S2 is equal to R of alpha square, E1 Y1 square plus E2 Y2 square. This is quite non-linear equation which we are going to solve over here. Now to represent all these equations in terms of the matrix, this is what the matrix will do. E1 y1 plus E2 y2 is equal to S1. E1 y1 square plus E2 y2 square is equal to S2. So this equation will be represented in terms of the matrix. Now here onwards the job is to obtain E1, E2, y1, y2 is already been done. So let's find out E1, E2. So y1 is here. Y1 square means alpha cube square means alpha raised to 6. Y2 square means alpha raised to 4 into 2, that is alpha raised to 8 means alpha raised to 1. So once we put all these values, S1 S2 is already calculated. Next we need to again obtain the inverse of this part and multiply it to this right side part. So by getting it, we can say E1 is obtained as alpha square and E2 as a alpha raised to 5. Now once this is done, what exactly the error polynomial? See here, E of x is equal to alpha square x cube. This is third location. Alpha raised to 5 and the fourth location. This is how the E of x is obtained. But after getting E of x, still we need to obtain the corrected code words. So that's why to get the corrected code word, just add R of x with E of x. After this addition, we will get the corrected code word. So once the addition is done with this part, we can easily understand how the corrected code word is same as that of the transmitted code word after correction. Okay. So after correction, obviously it is giving the cancellation over here. Means alpha square and this alpha raised to 5 means related to x cube and x raised to 4. We need to modify the terms. Means x cube. Let's proceed here. So x cube is nothing but with alpha square and x raised to 4 with alpha raised to 5. Okay. So here it is minus 1 and here it is plus 1. So if we trace it for the given values at the start itself, let's proceed. Okay, so here it was given, this was with received code word alpha raised to 6. Actually it should have been what, alpha raised to 5, and this alpha x raised to 3 should have been with alpha raised to 2. So that is what actually the thing which we need to trace out. So this is what done. So in order to have the corrected code word, afterwards we will get it with this kind of nature, which is nothing but the corrected code word by saying, let's say e of x plus r of x, which will give the corrected code word. So here we can just observe the corrected code word. So 0246135, this is what the corrected code word with the powers of x ranging from 0, 1, 2, 3, 4, 5, 6. So it is like this. So that can be compared over here also. If someone want to just cross check it. Okay, see here 0246135, this is what the corrected code was, but it is quite given in a disturbed format over here. 0246 then 135 means error was over here which we corrected. Okay, so this is what the locations where the error was and which we corrected. Now let's proceed for the second case of received code word. If you just look at the second code word, received code word specifically, for this case 0246135, whatever the transmitted code word, it is same as that of the received code word. But how to trace out this if it is not provided in the problem statement? Because each and every problem could not be with the encoding as well as with the decoding. So here, after R of x, we can obtain this related syndrome. But see here, S1 is with this value, S2 and S3 are 0. Since syndromes are 0, obviously the determinant will be 0 and no, we can say the error is present over here. So in the second code word, there is no error. So thank you everyone. Thank you for patient listening and all the best. Try to solve the many examples on the same principle and obtain the corrected code word. Thank you.